Hello! So far, our results about cores tend to be a little bit more complicated. In this lecture, we will discuss a clean result about cores, and that is, convex games always have non-empty cores. Recall that a game is convex if v of s plus v of t is at most v of s union t plus v of s intersect t for all s and t. Equivalently, this means that v of s union I minus v of s is at most v of t union I minus v of t for all s a subset of t, a subset of n minus I. This means that a player contributes more to larger coalitions. Now, convex games do appear in many applications. We will look at one of them here. Consider the bankruptcy game. Bob the banker is bankrupt. He owes 3 people money, $100, $200, and $300 each. But Bob does not have $600. He only has $200 in his name. So how should Bob's money be divided? There are many ways to do so. It could be 50, 50, and $100, or 0, 0, and $200. So which ones are stable solutions? Let's look at a general model for this problem. Bob has M dollars, and he owes money to N people, and the amounts that are owed are in this vector D in Rn. We will assume that M is non-negative and less than or equal to the sum of all the DIs. We will formulate a cooperative game as follows. We have the game NV where v of s is the maximum of 0 or m minus sum of di's for any I that is not in S. And this is defined for each subset S of n. The meaning of this is that the players are taking a pessimistic view. V of s is the amount left if the remaining players take all of what they were owed. So with the numbers above, m is equal to 200 and d is equal to 100, 200, and 300. And some examples of values are v of 2, 3 is equal to 200 minus d1, and that is 100. And v of 1, 2 is 0. As an exercise, show that this is a convex game. And here is the main result we have about the convex game. Convex games have non-empty cores. Now the proof of this is constructive. It actually produces a payoff vector in the core of the grand coalition. The idea is that the marginal contributions of the players in any permutation will form the payoff vector in the core. So here is our proof. Since convex games are superadditive, it suffices to find an x such that nx is in the core. So we only need to consider the grand coalition. Let sigma be any permutation of n. Without loss of generality, we may assume that sigma is equal to 1 to n. We now define the vector x by xi is equal to delta sigma of I, which is the marginal contribution of player I in the permutation sigma. There are two things we need to show. We want to show that v of n is equal to x of n, and v of c is at most x of c for all c a subset of n. The first part was proved when we tried to prove that Shapley values are efficient. X of n is the sum of the marginal contributions of all the players in sigma. And we proved that the sum of the marginal contributions is just v of n. For the second part, we let C be a subset of n. We suppose that C is equal to I1 to Ik, where these numbers are in ascending order, I1 less than I2, etc. Now, we are going to look at the contribution of Ij to two different coalitions. One is the set of all the players that come before Ij in a permutation. and the other is the set of all players in C that come before ij in the permutation. So what can you say about the contribution of ij to these two coalitions? We see that the second set is a subset of the first one. So, using the equivalent convex conditions, it means that ij should contribute more to the larger set than the smaller set. So, what we have here is v of 1 to ij minus v of 1 to ij minus 1 is greater than or equal to v of I1 to ij minus v of I1 to ij minus 1. So x of c is equal to the marginal contributions of I1, I2 all the way up to ik added together. Substituting the definition of marginal contribution, we get this expression here. And using our inequality, this is greater than or equal to this expression here. We see lots of cancellation in here, and we end up with v of I1 to ik minus v of the empty set. And this is equal to v of c, which is what we wanted. So that completes the proof. We note that any vector of marginal contributions is in the core with the grand coalition. The set of all the vectors in the core is script C, which is a polyhedron, and it is a convex set. This means that any convex combination of the marginal contributions is in the core. In particular, the vector of the Shapley values phi is a convex combination of the marginal contributions, so it is also in the core. Now there is actually a stronger result. The set script C is precisely equal to the convex combinations of all the marginal contribution vectors. There are no other vectors in the core, and we will not prove this result here. Back to our example in the bankruptcy game, the Shapley values are 33 and a third, 83 and a third, and 83 and a third. And this is in the core with the grand coalition. If we order the players in some way, say sigma is 3, 2, 1, the marginal contributions are 100, 100, and 0 each. So this is also in the core. And that concludes our discussion on the theory of cores. In the next lecture, we will go back to the matching game and discuss some of its properties.